So now we're dealing with, let's call this lecture 25, how to find residues. We now dealt with the residue theorem. So far, you may not find it so spectacular because you haven't seen it in action yet. You've just seen the theory. And you're probably still wondering, so how is this so useful? Well, you'll see as we go along. If you want to just whet your appetite, you can always flip the pages of your book or scroll on the PDF version and see where this is going. What kind of integrals will be handled with the residue theorem? That will give you a good idea of how powerful the theorem is. So let's take a few cases. One, if f is analytic at every point A, then the residue of f of z equals A is 0. And that makes sense. There's no coefficient of z minus A to minus 1. There's no coefficient of 1 over z minus A. It'll just have a power series expansion. So that the residue is 0. If there's no coefficient of 1 over z minus something, there's no coefficient, it's 0. Residue is 0. 2. If f of z has a shape something, say g of z over z minus A, where g is analytic at A, and g of A is not 0. In other words, there's no z minus A on top. If there were the z minus A, it will cancel. By saying g of A is not 0 means that there's no factor z minus A. It's called the factor theorem. You did that in high school, right? Remainder and factor theorem. Then the residue of f of z at z equals to A is simply g of A. You just plug it in the numerator and it's over. Okay, you guys are wanting a proof now. I wish you didn't ask me this, but since you insist, quick proof. So if I write f of z as g of z over z minus A, I said g of z is analytic, so you can write this as 1 over z minus A into, so g of z can have some expansion, a naught plus a1 z minus A, 1 plus a2 z minus A squared plus blah, 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 blah. And this is like 1 over z minus A. A naught is actually g of A. You plug in A and you get the first term. Let's remember Taylor series. The first term is f0 derivative. The second one will be g dash A over 1 factorial, z minus A. Third one will be g double dash A over 2 factorial. This is the expansion, explicit expansion. So, I'll just write it's obvious that coefficient of 1 over z minus A is g of A. It's this guy here. All the other ones will do some cancellation. This will cancel with that. This will go here and make this a 1. The next one will become 2. Only one term of 1 over z minus A. And in front of it will be g of A. That's easy. Like if I take some crazy function like, say f of z is ln sinh z over z minus 2. I can say the remainder or the residue of f of z at the point z equals to 2 is simply ln sinh 2. Let me deal with example 46 in the book, even though it's from the book itself. But I think you may find it a little tricky to understand, so let me deal with it. Example 46. Find the residue of sine z over z squared at z equals to naught. Now we're going to do the Laurent series expansion of this thing here. I'll do it in two ways, although the book has done it in one way. If I take sine z over z squared, 1 over z squared into what's the expansion of sine z? It's z minus z cubed over 3 factorial plus z to the 5 over 5 factorial, and so on and so on. That's 1 over z, multiplying it into the bracket, minus z over 3 factorial plus z to the 3 over 5 factorial, and so on and so on. So the coefficient of 1 over z is 1. That means the residue of sine z over z squared at z equals to naught is 1. If I expand the series about z minus naught, it will be z squared, etc. Then the coefficient of 1 over z is the residue. I'm just reading it. Multiply this in bracket. Alternative approach on the book. Sine z over z squared can be massaged as sine z over z all upon z. So it's like g of z over z. So, you see, I made it look like the theorem, g of z over z. So, I should actually put a 0 here, g of 0. So, res should be equal to g of 0. But g of 0 is actually sine 0 over 0, which is like 0 over 0. Doesn't make sense. We all know that 0 over 0 is what? 0 over 0 is, we all know that it is equal to, as we all know, it is equal to, come on, man. I knew you'd get stumped with a simple thing like that. What's 0 over 0? Is it 1 because anything divided by itself is 1? Is it undefined because anything divided by 0 is undefined? Or is it 0 because 0 divided by anything is 0? Which one of the three options applies? You guys didn't quite understand these things in first year. That's my gripe against you. Not against you, your teachers. The people didn't teach properly what this meant. 0 over 0, in fact, is any number. It's what we call indeterminate. You can't determine it. It could be 5, if you want. Why not? 0 over 0 equals 5. Cross multiply. 5 times 0 is 0. What number times 0 will give you 0 all the time? What number times 0 always gives you 0? Any number. So 0 over 0 is any number. It doesn't have a specific answer. It's indeterminate. But if we use limits, if we take the limit of sine z over z as z approaches 0, that we have shown in first year is equal to what? 1. That's 1. If you don't want to use first year calculus to prove that, you can use the L'Hopital's theorem. Remember L'Hopital's theorem? If it's 0 over 0, then you hit that with the derivative. Derivative of sine z is cos z over 1. Then you plug in 0. Cos 0 is 1. If you don't like L'Hopital's theorem, expand it as a sequence. Sine z will be this guy here. Divide this guy by z, you get a 1. Minus z squared, blah, blah, blah. When z approaches 0, all these guys die. Only the 1 lives. There are 3 ways I've shown you to prove this result. So, follows that the residue of sine z over z as z equals 0 is indeed 1. Another example, made up example. Find residue of 2z minus 3 over z minus I squared z plus 2 cubed at poles or singular point. So firstly, let's work out the poles. The poles will be where the denominator becomes 0, z equals to I, and z equals to minus 2. Now, I can hit this with partial fractions and say, by partial fractions, I can write 2z minus 3 over z minus I into z plus 2 cubed in the shape of, or I had a square. I can have it as a over z minus I plus b over z minus I squared plus, now that finishes off the z minus I business. Then I have c over z plus 2 plus d over z plus 2 squared plus e over z plus 2 cubed. Partial fractions. And in case you're getting a bit ticked off and saying, wow, that's not an infinite series, man. Thereafter is 0 over z plus 2 to the fourth plus 0 over z plus 2 to the power fifth. Then typically we say infinite series. You remember partial fractions? If you've got things that are repeated roots, like a square, then you break it up as a over z minus I plus b over z minus I squared. What if the root, what if the stuff is a quadratic, like it's not reducible, you can't factorize it? Then you write this bz plus c, isn't it? And you do that in first year. Let's not go there. Now, if I want the residue of f, let's say at z equals to I, what is the highest, what is the coefficient of 1 over z minus I? The answer is A, this guy here. That's the coefficient of z minus I to the power 1. If I want the residue of f when z equals to minus 2, the answer will be C. The number on top of z minus 2, z plus 2 rather, it'll be C. Okay, so it will be C. The other ones don't matter. According to the residue theorem, the residue is a coefficient of 1 over z, or 1 over z minus something, to the power of 1. Not 2, 3, 4, and so on. Those don't count. Any questions? You'll see this is quite easy It sounds a bit complicated now because I'm going through many different types and stuff. But at the end of the day, you identify 2 or 3 approaches and use it all the time. Even if there's a simpler way, somehow you guys will go for the standard technique. You'll see it's not so difficult. Just bear with us there for a while. It's actually quite easy later on. Here's another nice result. If near a point A, f of z is p of z over q of z. In other words, it's a rational function where p and q are analytic, but q of a is 0. That's where you get the poles, denominator equal to 0. But q dash a is not 0. The derivative is not 0. Then the residue of p over q at z equals a is p of a divided by q dash of a. P of a divided by q dash of a. If you've got a rational function, something of z over something of z, and you've got all these poles when q of a is 0, and z minus a is 0. There could be many of them. We know to handle many of them, you write you sum them. Let me give you a quick proof of this. Proof. So f is p over q, and we said it has a power series expansion, so you can have it as p of a plus p dash of a over 1 factorial plus p double dash of a over 2 factorial. This will be z minus a, by the way, z minus a. Here it will be z minus a squared plus blah, blah, blah. Likewise, at the bottom you'll have q of a plus q dash of a over 1 factorial of z minus a plus q double dash of a 2 factorial z minus a squared plus blah, blah, blah. Then you'll say, but q of a is 0. So f boils down to p of a plus p dash of a z minus a p double dash of a 2 factorial z minus a squared plus blah, 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 all upon q dash of a z minus a plus q double dash of a over 2 factorial z minus a squared, and so on and so on. At the bottom you can have, so on the top you have p of a plus all that stuff there. At the bottom you can take out z minus a as a common factor and get q dash a plus q double dash a over 2 factorial z minus a plus all that the stuff there. So now take the limits of f of z as z approaches a. We then get all these other terms here with z minus a and 2 as it goes towards a will be 0. This one will survive here. So this one here alone will survive. The coefficient of 1 over z minus a, we will get, let's write it as, what happened there? We will get coefficient of 1 over z minus a to be P of A over Q dash of A. Remember, Z only approaches A. Z doesn't equal A. Z minus A survives. But the powers of Z minus A become close to 0. In other words, this guy survives. This over that. That becomes a coefficient of 1 over Z minus A. If you don't like that explanation, I can expand this guy here, 1 over this guy in the power series, like I did for the 1 over 1 minus cos Z problem. Remember, I had this A plus BZ squared plus C, Z to the fourth, etc. Similar explanation. Yes. That's it. Take an example. It's always easier to see the thing in action, then you understand it when there's an example. Say f of z is z cubed plus 2z over z squared minus z minus 6. So find the residue at the singularities. So far we're just finding residues. Later on, the game will be to find an integral because the integral boils down to finding a residue. That's the residue theorem. The contour integral of f of w dw is the residue. So now I'm just teaching you how to find residues. So yeah. Solution. So the poles are z squared minus z minus 6 is z minus 3 into z plus 2. The poles are z equals to 3 and z equals to minus 2. So the residue of f of z at z equals to 3. So you see it's like p of z over q of z. Something divided by something. According to this result here above there, when you plug in 3, of course, this becomes 0. It's one of the poles. All you should do is have f of p of a, plug in the 3 over here, differentiate the bottom and plug in the 3 there. Game over. That's the method. So you will have z cubed plus 2z over, differentiate the bottom. Differentiate the z squared minus z minus 6. This is 2z minus 1. And plug in the point 3. Game over. 3 cubed is 27 plus 2 3s are 6. Hey, there's so many emails. 27 plus 6 is 33 over 2 3s are 6 minus 1 is 5. So the residue is 33 over 5. If I had to expand this out, the coefficient of 1 over z minus 3 would be 33 over 5. I don't have to do the expansion. I've got this theorem to rely on now. Of course, if you want to do the power series expansion, you can do it. You get the same result, guys. The residue of f of z, this time when z is equal to minus 2. You take this, it's the same thing. It's p of z over q dash, p of a over q dash of a. So it's z cubed plus 2z over the derivative, 2z minus 1. And you just plonk in minus 2. It's minus 8, minus 4 is minus 12. Minus 4 minus 5. So it's 12 fifths. You see what I mean? When you see an example, it's so much easier than looking at the proof. All you have to do, if you have if you have some, hey, where's this email? if you have something divided by something, so at a singularity, you plug the singularity in the top, differentiate the bottom, and plug the singularity in there. Gives you the residue. That will be the answer for some integral later on. All right, now we end off with the question we are thinking about, but you're not asking. What is the next natural question? We dealt with how you have, let's say, z minus a in the bottom together. We dealt with z minus a, z minus b, z minus c. Many poles you can find them in a find each singular, each residue in element. What is the question that remains now? What type happened at one? You seem like a mathematician. You're covering all the different types of functions. I haven't done what happens when you have like a z minus 3 squared or z plus 2 to the power 5. So there's a repeated factor. That's the last type I will deal with, and that comes from a beautiful differentiation formula, unexpected, not unexpected. Let me end off with that. This is the fourth. Poles of order more than one. Example, f of z equals to something g of z over z minus a power n. What if you have a repeated pole? That's a question. Well, so f of z can be written as g of z over z minus a to the power n. If I expand the top, it will be g of a plus g dash a over 1 factorial z minus a plus g double dash at a z minus a to the power 2, and over here you'll have 2 factorial plus blah 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 blah. All upon z minus a to the power n. Right, now let me cut to the chase here. So on the top you'll have g of a plus all that stuff. The last one here will be the nth derivative, z minus a to the power n, and you'll have divided by n factorial. Isn't that so? If you carry on, like the second one here, this is the 0 first one. The last one will be the nth one. I have 0 here. That's the 0. The last one will be n derivative over n factorial z minus a to the power n. Over z minus a to the power n at the bottom. If I divide this guy into that, notice that we cancel off. We cancel off. I can divide this into each one of the terms. Really one thing at the moment. When I come to the last guy, let's drop this easy again also. When I do the last one, you cancel off. So that will give me that will not give me what I want. I want to make sure there's z minus a at the bottom. Z minus a to the power 1. 1 over z minus a. So can you see that I write the term before this? The n minus 1 in it. So that will give me the coefficient that I want. So the one before that would have been the g n minus 1th derivative over n minus 1 factorial z minus a to the power n minus 1. That's the guy I want. That's the kingpin element here. So when I do this division, I will get stuff. Plus, at that stage there, I will get g n minus 1 over n minus 1 factorial. What will be the thing there now? Will it not be z minus a here at the bottom? Check it out. If you have z minus a, n minus 1, over z minus a to the power n, n minus 1 minus n is minus 1. So then the coefficient of 1 over z minus a is static. N minus 1 factorial, the n minus 1 derivative divided by n minus 1 factorial. So I can say in conclusion for this part that the coefficient of 1 over z minus a is n minus 1, the derivative at a, divided by n minus 1 factorial, and that is the residue. In other words, the residue of g of z divided by z minus a to the power n at the point z equals a is simply 1 over n minus 1 factorial, the nth minus 1th derivative of g of z at z equals a. So if you've got a term like 1 over z minus 2 cubed, then you have to do the derivative twice. Second derivative of the numerator and plug in z equals a. Then it's finished. Okay, so there are many examples that can be done in this. I think I'm going to go into the next part of this here. I will stop here at this point. Unless you want to go on. Now, the next part is the next section will be finding integrals. You will boil down to all these cases here. You will eventually come down to finding the residue of this type z minus 3 to the power 7. When you do the sixth derivative of the numerator, oh, that's factorial here. Don't forget the factorial, n minus 1 factorial. Plug in z equals a, and we're done. So, unless you have any, you can just write this one line here. I don't like writing this line, but it's expressed like this in the book. I don't like it. Or you can say the residue of f of z as z is a is 1 over n minus 1 factorial dn minus 1 dz n minus 1 of z minus a times f of z at z equals a. Because g is actually z minus a to the power n of z. But focus on this part, this form here. That's better. It's easier to follow. Let's stop there.